Okay, so where we ended off, we were talking about iterators, and we talked about how amazing they are because they provide us, just by adding this like another layer between the actual iteration and how we interface with iterating, we eliminate the differences. Like we somehow we create specialized tools for iterating over various collection or containers, and then we can interact with them to iterate the exact same way, which enables a lot of power. And one of the awesome things is now it actually gives us a common way to iterate over a stack, regardless of if it's an array stack or a linked stack. Same with a queue and so on. So we could actually do an equals check on stacks and queues, where before we couldn't really. We could only ever compare array stacks or linked stacks, but not to each other. But we ought to be able to. Okay, so next, exceptions. Before I carry on, are there any last questions about iterators or anything? Okay, so we've talked about exceptions before. We talked about them in 161 at a pretty high level, and we're going to talk about them at a similarly high level here right now too. I'm just going to talk about them a little bit in Java. There's not going to be much of a difference. The motivation for them are the same as before, and we've definitely come across exceptions before. There are various different types of exceptions. I mean, there's like array index out of bounds, divide by 0, file not found. Like there's a lot of exceptions you've probably come across. We've even written code that throws exceptions in various cases, like what happens if you try to pop from an empty stack, right? We throw an exception. Now, some of these exceptions are exceptions that that might just mean, I'm trying to think of a good example right now. Some of them are exceptions that like you have to deal with, right? You ever notice that sometimes you're using some code that might throw an exception and you have to put it in a try catch. If you don't, it won't work. It'll say it has to be in a try catch. Like the IO stuff, right? We did the IO stuff and that had to be like try catch. Unless we did that cheesy thing where we just kind of like pass the buck by saying main like throws exception. But some exceptions like you really have to like deal with, and other exceptions like the ones that we included, and there are keywords you put into your code to make it such that someone needs to put a try catch, right? It makes them be very intentional with their code. But some of the exceptions that we've used, like throw whatever exception we did, like can't pop from an empty stack. That one, you never needed to put your pop in a try, right? You just didn't. But the assumption would be like, if that ever happened, the program's going to crash, and really that's like the programmer's fault. Like someone did something such that you used it wrong, right? But like if there's like a file IO exception, like that really might not be the programmer's fault. That might be something else. And so like those exceptions should be caught and handled a certain way. It all comes down to like the spirit of what the exception's trying to do. Anyways, exceptions provide a nice way to logically separate. Let me take a step back. There are a lot of people out there that all of this motivation for why we like exceptions, there's going to be a lot of people out there that go like, and for all those reasons, that's why they're terrible. Because exceptions are like very side effecty, and there's a lot of reasons why exceptions maybe are a bad thing to use in programming. They're not really, but from a more like fundamental perspective, maybe there are some interesting arguments there, but we're not going to explore that right now. All right, so exceptions provide a nice way to logically separate like our regular normal code versus the like exceptional situation. Like, here's how you pop from a stack. Yeah. Oh, but you know, if so this funny thing happens, here's what you do. Right? It's got that nice separation. And it really makes it easy to like exceptions themselves, you can think of them as these like little balls, right? Whenever something happens, we create this little ball that has a message attached to it. And if I create an exception, I give it to somebody else to deal with. And when they catch it, they might not actually be the ones dealing with it. They might propagate it up to whoever told them to do something. And then maybe they deal with it. Because you figure like when you call a function, it might call another function, that might call another function, that might call another function. Maybe this function throws an exception, but it's not until like here where we actually deal with it. Like there's a lot of nuance to it. But at the end of the day, exceptions make an easy way to do that. It also allows for like differentiating between exception types and how we might want to deal with certain things in a certain way depending on what exception was actually thrown. Because maybe you have a chunk of code that throws an exception A under one condition, but exception B under another condition. But what do you want to do if exception A is thrown versus B is thrown and whatnot? Now, exceptions actually fit into the Java object hierarchy. Exceptions themselves are objects. They are a subclass of a throwable, which is a subclass of an object. All right, and exceptions are what we're used to dealing with. There's runtime exceptions and other exceptions, and we can talk about this more a little later. Now, you'll notice, though, that there's this thing over here called errors. Now, you might remember in Python, all the exceptions are actually called like errors. Now, in Java, errors mean something a little bit different. Really, in Python, errors really mean exceptions, because I think Java kind of makes a little bit more sense in general, but whatever, maybe it's a semantics argument. Errors are a little bit different than exceptions. When you get an error, something bad happened and it wasn't your fault or anybody else's fault. Something weird happened. It's like an unrecoverable situation, right? Like maybe your computer ran out of RAM. Well, what are you as the programmer going to do about it? Nothing. You can't. You're stuck, right? You can go add more RAM, but what are you as the programmer going to program into your code to give yourself more RAM? It's not going to happen, right? Yeah, got to go download the RAM. So errors, okay, in Java there's two classes that are throwable. A throwable object is basically one where you use that throw keyword. Errors are one of two throwable classes. Errors typically, you can't recover from them. Very abnormal situations. Typically, you're not going to catch and handle these errors. You're just not going to. Errors are regarded as what we call like unchecked for the purpose of compile time stuff. To understand why these are not caught, like here's what I was saying, like the out of memory error. If Java's virtual machine runs out of memory, you can't just magically allocate more memory at runtime to deal with it. You can't, right? So, you're stuck. So you can't do anything, whatever. Errors, if you ever see a Java error, congratulations, you don't see them very often. It's a very magical experience. Try again and hope for the best. Now, exceptions, on the other hand, are ones that maybe we can catch and handle. Now, some of them you ought to catch and handle, and other times maybe you really shouldn't, right? Like if you try to open a file that doesn't exist, well, maybe you try to catch it and handle it, and you just say like, file not found. Or maybe you're a helicopter, read the sensor again so I don't crash. Whatever, right? But some exceptions are things like, oh, you indexed an array out of bounds. Well, you probably messed up as the programmer. So like, what should the code do at runtime to deal with an array index out of bounds? Maybe there are cases where you really do want to catch where an array index out of bounds happens and your code does something differently. I don't know. But usually that's not something that you're going to want to like usually there's something wrong with your code in those particular examples, like popping from an empty stack. Usually there's something wrong with your code. Maybe you didn't say like, if not empty, pop, right? So those situations, often we're not going to try to like catch and handle them. Where other exceptions, you do want to catch and handle. There are probably cases I can imagine where really you do want to catch and handle when you pop from an empty queue. That's fine, but generally speaking, the idea of these exceptions there's a bit of a difference. Hopefully that's kind of clear. So, okay, below are the remove and remove first methods from the array sorted bag. Okay. Remove does not throw an exception, but remove first will if trying to remove from an empty bag. Okay? Okay, the exception being thrown by remove first, no such element exception, the Java exceptions have a class hierarchy. There is a hierarchy. There's like runtime exceptions, and I guess below that would be a no such element exception. Okay? So it is what we call an unchecked exception. We don't have to throw it in a try-catch thing. So the method does not need to include throws runtime exception in the method signature. What I mean is, if we wanted this to be a checked exception, what I would say, I would write public T removes first, throws no such element exception, When that's in your signature, it means that somebody must put try, catch around this type of stuff. But here, we're not going to force them to do that, because often removing first from an empty thing, chances are that was the programmer's fault and not something that happened at runtime that was peculiar. So the motivation for using exception in remove first is, when removing from an empty bag, what should happen? Perhaps this means some critical error happened and the program must stop, or maybe the program using the bag can just ignore it, or maybe whatever. We don't really know, but whatever. Either way, as the writers of array sorted bag, it's not possible for us to know what you want to do if you call remove first on an empty bag. Maybe you really messed up, or maybe it wasn't a big deal. Who knows, whatever. You can deal with it if you want to. So all that we can do is throw an exception to let you know, the programmer, that you're using the class I wrote and something funny happened. You might wonder why the more general remove does not throw an exception. Well, first of all, this is conforming to like the basic Java collection thing where your add and remove returns a Boolean on success or fail. We could very well write another version of this that doesn't return a Boolean and maybe just does throw an exception. That's actually not that crazy. There are some examples we saw in like the Java queue interface where there was like remove and pull or something. I can't remember what they were actually called, but one was like remove the element and return it, and if it was unsuccessful, return null. And the other one was remove the element but throw an exception if something funny happens. It gave you the choice as the programmer. If you're like, well, why do I care? I don't know, maybe you do. It's a choice. You can use one or the other, right? Does it matter? Maybe for you it doesn't. Maybe it does. You've got the option. Yeah?
Is there a way for an interface to be like, hey, you need to implement one of these two methods?
I don't actually know. Maybe? Interesting question, but I don't know. Like, you must implement it, like at least one. But not neither. You could do both. Yeah, I don't know. I don't actually know. So yeah, and here in the case of like, well, if remove fails, return false, right? Like that's what's going on here. And this actually conforms to like the basic Java collection thing. Is it better than throwing an exception? No, it's just a different way to do it. It's fine. What else do I say? Return type, yeah, so it returns false. The expected return value of remove first, and yeah, and so why does this one? Well, here, the expected return type is not a Boolean. So I don't have like a Boolean to tell me like success, fail. I have like, do I have the thing or not? Now, I could return null, or I could throw an exception. Which is better? I kind of like the exceptions, but, you know, to each their own. I think a lot of people would probably say this is like good, but again, to each their own. And yeah, like I said, this conforms to the Java's base collection interface. If you go like in the Java hierarchy, collection is somewhere near the top. In fact, oh my goodness, go away. No, go away. So we actually have iterable collection. So iterable is actually well, this comes from the iterable, which, okay, we want our collections to be iterable, queue, cool. And then under there we have like list, queue, set, and then we have like more and more specific. So near the top of this is collection, which is gonna have like, so iterable, we know what that has. It has you must implement a method called iterator that returns an iterator, that's all. This is gonna have things like add, remove, general stuff that a collection has. And then as you go down, you get more and more specific. So if we go back here, we see like remove Boolean. Like this is pretty normal stuff, right? So a general collection, Boolean, true if it was successful, false otherwise, right? This is like the kind of like standard, typical what Java would do, and it's kind of nice to conform to like Java's for consistency purposes. And who decided that? Nah, the good people at Java. So anyways, however, it would not be wrong to have the general remove throw an exception in this situation. In the end, this really is a design decision. Is one better than the other? Maybe. I don't know, it's hard to say. It's up to you. To each their own. And notice the string provided in the exceptions constructor. Where? Empty bag. Yes, right here, empty bag. Exceptions, by the way, this is a constructor. Like, look, this right here, there's a lot going on here. You've been writing this code in several cases, but like, look, this is a call to a constructor of an object that happens to be an exception, which is an object. So this is the constructor for a no such element exception. And this constructor takes an argument. It actually has several variations with different arguments that it can take, but one of them, if you give it a string, that's like the message for the exception. You don't need to have one in there, but if you do, it's kind of nice, because if this exception gets thrown and is never caught and your program crashes, you will see like no such element exception thrown, empty bag, right? Like it gives you a message, which is a little bit more handy.
Are there any other inputs worth knowing other than the string?
There is There are, I just can't remember them right now. Because there was, I think there might be an example of one. What's kind of neat too is when you catch an exception, you can get like a stack trace from it. Like when you catch an exception, you can, maybe we actually do cover some stuff. I can't remember offhand, so now you're making me think, when you say like, if I can't remember them, maybe the answer is no. I don't know, but you know. Anyways, the new keyword also gives away the fact that, yeah, we're creating a new object, this exception. And we're throwing it, so whatever. Throw is kind of like a return, but for exceptions only, yeah.
It might not be a no, but it's certainly not a strong yes.
Yeah, fair enough, yeah. So the string is the message the exception provides to give detail here. This is, okay, hold on. Let's see. Maybe I'm misremembering. Maybe I'm remembering more about what I can get from an exception. Oh, come on. You can give it causes. Look at that. There you go. What do we have here? We have a default, one where it takes a string, and a throwable thing called a cause, which calls the superclasses. So this would be a throwable thing. That would be like an exception or an error. So you can actually have an exception, take another exception that it's like, well, here's why I threw this exception. And sometimes that's handy, where like, if I call this method, that gives me this exception, and then I go like, so I can return this exception to you, or I can provide maybe more context and create another exception, but give this exception to this one, and then give it to you. So now you kind of have two exceptions nested. That's kind of cool. That's what I was thinking of, the throwable. You can also give it just throwable, and you can also just give it the string, right?
Yeah, that's worth knowing.
Yeah, and here you might be going like, what's the super? Well, it's calling the superclasses, which is a runtime exception, which is super, yeah. And then you're like, whoa, the runtime exception just calls its parent class's constructor. You're right, it's just it's an exception. And you're like, wait, that's just calling it super. And then you're like, yes, it's a throwable. And there you go, right? So if it takes, yeah, anyways, there you go. Pretty neat stuff. There we go. Exit. All right. So, okay, yeah. So consider how array index out of bounds exception provides additional detail when you do it. Like, you know how like when you get an array index out of bounds, your computer doesn't just say array index out of bounds. It says array index out of bounds, like -17 is not a valid index, right? Like that's the message. Whatever it actually says, I can't remember. So that's how we throw an exception. We create a new exception, we throw it. So how do we catch an exception? Like if someone's using the array sorted bag, what are they going to want to do if the exception gets thrown? And they want to handle it a special way. Like, what do I want to do if I call remove on an empty array sorted bag? What should be done if calling the element doesn't exist within the array sorted bag, right? So like, I need to deal with these exceptions. And there's actually two different cases that might cause an exception from this class. I could get an exception. Oh no, what should be done if calling this must be based on an old version. I need to get rid of this line here. The old version did throw an exception on the remove. And this one's fine, so ignore this. Speaking of, ignore. What I'm saying is an older version of the code for this course did have the general remove, or the remove a specific element, not return false, but return, like throw an exception if it didn't exist. Anyways. So yeah, what should happen when something bad happens? We could ignore it. Maybe it doesn't really matter. We'll never try to catch the exception. If the exception is thrown, the program will crash. We'll see the message, but it doesn't really matter. This should never happen, so if it does happen, I want the program to crash, whatever. Cool. So since the exception is not caught, the exception would get propagated from every calling method all the way. Let's say I'm main. I call a method, that calls a method, that calls a method, that calls a method. That might throw an exception, okay? This exception gets thrown to the calling method. They get it. If they don't handle it with like a try catch, if they don't handle it, they're going to throw it to the calling method. And they're going to keep doing this all the way back to main. And then this exception gets to me at main. And if main doesn't catch and handle it, it throws it to the caller. But who is the caller of the main method? You, the programmer. That's why you see unhandled exception, crash, whatever, whatever, whatever. Okay? So yeah, since the exception is not caught, the exception will be, whenever the exception is called and is never caught, it keeps getting propagated all the way back, right? It gets caught, this will keep happening until the exception is caught somewhere, or it gets to the main method, which also doesn't have to deal with, which also doesn't deal with it, which then returns it to the user, and the program crashes. What else could we do? Well, maybe we stop immediately, right? If I try to remove an element from a bag, and I see a no such element exception, I gotta stop. Maybe this is important, maybe it's about to do some radiation therapy on someone and I don't want to apply the wrong number. Or if something bad happened, do not apply a bad dose of radiation, right? Now here you're like, what's some cleanup? That's just some whatever. Maybe, okay, wrap things up, stop, right? Maybe you can just catch it and you carry it on. You carry on, right? You try it. Maybe if you try to pop from an empty stack, okay, something funny happened. Not that big of a deal. I'll just make sure the program keeps running. Like maybe it's to keep your helicopter in the sky and it doesn't crash, right? So yeah, something funny happened, but you can effectively ignore it. So what do? We try. If something bad happens and we catch that exception, we can maybe print like, oh, something happened. And we can also like, this is what's kind of neat here, by the way. You'll notice in the syntax for a catch, it's catch type E. E is a reference variable to the exception. And we can actually ask E, what's your stack trace? I could say E.print stack trace. Now you'll notice this doesn't return a string. Maybe it should, I don't know. But print stack trace, and this will actually print like where in your code. Like if you had a method call a method call a method call a method, it would say, I crashed in this method, which was called by this method, which was called by this method, which was called by this method, and so on. Which is kind of nice. Or maybe what you can do is rethrow. And here we go. This is a perfect example of what to do. So sometimes maybe you catch an exception like an empty bag exception, and this exception gets returned to a method, and this method was doing something super important where there's a lot of context about how this could happen. So maybe what I'm going to do is I'm going to make a new exception of a different type, but put that exception that I just got inside of it to add just additional context to what happened. So this is an example of another type that could be given to the constructor right here. E is a throwable object, an exception. Any questions about any of this? I realize this is effectively review with some Java syntax, but you've already probably seen this in various cases already. Now, sometimes it could happen where you call a method and this is very important. So listen up. Sometimes it can happen where you call a method that can throw several exceptions, several different type of exceptions. So maybe you call a method that might throw a array index out of bounds exception, a no file found exception, whatever. A bunch of different types of exceptions can come from one particular method call, right? And maybe, depending on what exception I get, I need to handle these exceptions in different ways. Okay? So if I call a method that's like called may throw various exceptions, and I get back an exception A type, maybe exception B type, A, B, exception C type, whatever, this is effectively like an if statement for exceptions, like an if block. If I see this one, or maybe if I see this one, or maybe if I see this one, I will handle the exception based on what type it is. This might throw an exception A, B, or C. If it gives me back an A, well, I deal with it this way. If I see a B, I deal with it this way. A C, I deal with it that way. There's also this finally thing here, where this is some code that will always be run. Sometimes you don't see it that often, but sometimes you've got some maybe some special cleanup code that needs to happen if something funny happens. But what's neat here.
Hold on. So that finally only happens if there was an exception at some point?
Yeah.
Okay.
So where do I say? And finally, sometimes it's necessary to have some code run regardless of if an exception was thrown. Oh no, I guess maybe this is a do it no matter what.
Then why would you write finally and not just not write in a block at all?
I'm doubting myself. Check it for me. Does finally always run? And then once I have the answer, maybe I can reason why in a moment. So with multiple catch statements, though, this is very important. And by the way, this goes to show how often you use these things, right? You know, I don't really think about them very much. Here's a very important concept. Because exceptions follow the class hierarchy, we have to be very careful of the order of how we catch them. These catches are kind of like exclusive ORs, okay? Or like mutually exclusive if statements, like else ifs, else ifs, else ifs, where only like one will run. Because they follow the class hierarchy, consider an IO exception and a file not found exception. A file not found exception is an IO exception. We could also consider the no such element exception and runtime exception. A no such element exception is a runtime exception. If we did it in this order and I get back a file not found exception, Java's going to go, oh, because it checks them in order. It's going to go and say, oh, a file not found exception is an IO exception, so I will handle that this way, and then stop looking. But really, you wanted to deal with it in the more specific way if you had a file not found exception. So you have to be very careful of the ordering. I think IntelliJ actually warns you of this now, of like, uh-oh, you have a less specific thing above a more specific exception type. But long story short, you have to be careful of the order of these things. You want most specific to least specific. Yeah?
So if you use a finally block to make sure the code always runs, because if in your exception handling you had a return or it throws another error, or sorry, another exception, then the finally block will still run before that actually gets returned. That's what I've gathered.
Oh, okay, so it's going to run no matter what before it actually like crashes or breaks or something. And it's important that it's there and not just after, because then it won't run.
Yeah, because then if it returns something,
yeah. But if nothing bad happened,
then it still runs anyway.
It still runs the finally?
Yeah.
Okay. Sure.
Yeah.
Okay, cool. Is this point here is actually quite important. Is this point clear? If only one of these, if I get a file not found exception in this chunk of code, I will say, hey, it's an IO exception, I deal with it like this, and then I skip everything else and carry on. But what I wanted, if I see a file not found exception, I want to deal with it this way. I will never get there because this catch will deal with it first. So in order to deal with it, you want to put it in reverse order, where you want it to check file not found exception first, and so on. Yeah? Yeah? Good? Good. Oops. All right. There. That's your blitz reminder of exceptions. Now, I just made a point to say, like, sometimes you have a program that calls a function, that calls a function, that calls a function, that calls a function. And the computer actually needs to keep track of, like, okay, well, this function called this function, which called this function, which called this function. So when this function finishes and it returns, where does it return to exactly? This is a very important thing that we need to deal with. In fact, this concept is actually a very low-level concept, where this is not like a Java idea. This is more of a how our computers work kind of idea, but more on this as we go. So, programs use and access memory, memory being like RAM, for example, in different ways. Now, typically in the computers that we use today here, this is not a requirement, but based on the general design of all these computers here, they follow, at the end of the day, they follow this general idea of a von Neumann architecture, as opposed to another popular architecture, the Harvard architecture. Now, these architectures of how these computers work were designed decades and decades and decades ago. Long story short, the von Neumann-based architecture has a shared memory space where the same chunk of RAM, okay, all of your RAM that your computer uses, is used to store both instructions, like your program, the instructions of your program, but also the data at the same time. So it has a shared memory space, okay? So, for example, if your program's like, instruction 1 is, oh, load data into my computers have like these things called registers, okay? So you have like a hierarchy of memory, let's say, but very simply you have like RAM, right, which stores data and instructions. And you also have things called registers. Registers are like, it's like RAM, but can only store like one piece of information at a time. But it's within the registers, that's what like your processor is acting on at the same time. So if you want to add two numbers together, you will get a number from RAM and put it in a register, get another number from RAM, put it into a register, add them together, and then maybe put it back into RAM. Okay, so registers, like RAM would be like my table, if I'm making a cake, RAM is like my tabletop, and the registers are like my hands, right? Like if I want to do things, I got to use my hands to do it, okay? But like everything that I need is here for me. Like I've got it out, I can access it pretty easily, but in order to do anything, I got to put it in the specialized registers, okay? And then like your hard drive's like your pantry and fridge, right? Where you're like, okay, sometimes you got to go get some stuff and put it into RAM, put it on your table, right? Anyways, so you might have instructions. Now, when you write instructions in Python and Java, we are writing instructions at a very high level, okay? But your computer, when you say like, oh, system.out.println, if you go to your computer and you say, hey, system.out.println, your computer's going to go like, what the hell is that? I only know what low voltages and high voltages are. That's all they know. So there's a lot of steps that actually go from the Java code or Python code to what your computer can actually understand and run on its hardware through its processors. So we're used to this, but like if you consider what your computer's doing to run things on hardware, because that's what's happening, these zeros and ones, low voltages and high voltages, are moving through the circuitry on your computer to do all the number crunching. So your instructions are things like, okay, load a value from memory address whatever into register A, load a value from memory address wherever else into register B, add them together, put them back into there. Now, when I say load the value, the instruction is load some value into register A. The instruction is load some value. The data is the value, okay? And that value might be like, so really what your instruction might say is load the value stored in memory address 1 billion into register A. Okay, so I looked at the instruction that was stored in maybe RAM address 1. And it says, go to memory address 1 billion. Okay. Take it, that's data, and put it into the register. Instructions and data. They share the same memory space, physically. The Harvard architecture is different in that it actually has 2 blocks of RAM that are physically separated, and they have different signal designs and whatnot, where the instructions are stored over here and data are stored over there. There are pros and cons to both. And the features of one over the other actually allows for some fun nuance, but that's not the point of this class. Anyways, we have the von Neumann architecture. So we have data and instructions sharing the same memory space. However, we like to pretend we don't, because having your data and instructions share the same memory space is a bit of a recipe for disaster. It's prone to problems. So we like to pretend we don't. We do what we can to try to separate these things. Even though they are in a shared space, we do everything we can to think of them as separate. And we are interacting with these computers at a very high level through a language like Java. So there's a lot of layers between us and the hardware, for better or worse. And in those layers, like in the Java programming language, it does a lot of the heavy lifting for us to keep these things separated. So Java actually does a lot of memory managing for us, where it's like, okay, this chunk of RAM, I'm just going to store my instructions, but over here I'm going to store data. Yes, it's a shared space, but as far as I'm concerned, we're pretending they're separate. So yeah, having a common memory space for instruction data could be a recipe for disaster. However, modern computer systems have a lot of strategies to mitigate any potential issue here. So in many programming languages, Java included, memory is logically separated. Often it's also technically physically separated in that they try to take chunks of RAM, where it's if I've got RAM, maybe here I'll have instructions and here I'll have data. And this is memory addresses 0 through 999. I picked these numbers. These numbers are not meaningful in any way, so don't think that they are. And then from here I'll have 1,500 to who cares. RAM goes on forever, right? So, and then this chunk right here we leave empty. It's not needed. And look, it's physically separated because there is a physical separation. But we'll say here logically separated, because really a lot of weird fancy stuff. Look at that wasted memory. We want to use it, and maybe we need to get really weird how there's multiple different blocks of RAM. There's a lot of crap that we don't need to deal with, thank goodness. Oh, look, we've blocked so many ads from you. That's a good amount of ads. Anyways, so Java does a lot of work for us to separate things, right? So there's instructions, things like our classes, our interfaces, code, what are the instructions? And then there's this chunk of RAM that's allocated for dynamically allocated data. So memory being allocated at runtime. So maybe my program says go and generate this data. Well, where am I going to store the data that's generated, right? Well, it's going to store it in some chunk of RAM. And then there's going to be program elements related to what is currently happening. Again, like I was saying, when data is being used, where is it going to go? So, by the way, this topic is being kept at a very high level intentionally. Going into the details of this is far outside the scope of this course. We would be getting into the nuance of how Java does it, which is not the point of this course. The point of this course is data structures, but having an idea of how this works is important for where we're about to go. So I'm keeping it at a high level intentionally. So don't worry if you're left going but how? We really don't care right now. Yeah? Oh, I'm sure. I know, anyone can go build something like that, right? Yeah, I can't think of anything off the top of my hands, but there's definitely plenty of things that do. You just have to have an instruction set that can handle that type of stuff. Now, keep in mind, when we say we use the von Neumann architecture, look, in terms of what the definition of a von Neumann architecture is and how these things work, it's pretty separated. But at the end of the day, it's still based on that idea, but there's a lot of no, really there's a lot of extra steps and whatnot that were never formulated at the time. Yeah. It's probably good to not get too bogged down by these definitions. Really the thing is shared memory, not shared memory. So, Memory is broken down into two broad sections. This is not just true for Java, it's true for a lot of high-level programming languages. We have the stack, and then we have the heap. Now, if this was a programming language like C++, you're mad. Maybe not mad, but having a really good understanding of the difference between these things is very important in a language like C++. Because, as you know, when we had, let's think of expand capacity. You had reference to an array. You called expand capacity. You need a new array. So your field, everything gets copied over, then the field that references that array updates to the new array, right? What happened to that old array? We created it. We made it. It was size 10. We needed something of size 20, so we updated. But that old array of size 10 is still kicking, right? It's still there. It's in RAM somewhere. But Java goes, okay, look, nothing references that array, meaning the program can't use it, meaning it's as good as gone and it's just wasting space, meaning get rid of it. It doesn't matter. Now, the computer's not going to waste time and be like, that chunk of RAM, let's assign all the values to 0. Like, no, it just goes like that chunk of RAM is rewritable. Whatever's in there, it's garbage, it's irrelevant. I can overwrite whatever in there. A language like C++, depending on where things are, in the stack or in the heap, a language like C++, if you did something like that, we're left going like, well, hold on. Depending on where it is, that chunk of memory, you've got what we call a memory leak. That chunk of memory was allocated. The computer's not going to delete it for you. C++ is not going to delete it for you. You lost reference to it. It's now in RAM. It's taking up space. Your computer knows not to overwrite it because it was important, but you don't really know where it is. You can't get to it. It's a waste of space. That's a memory leak. So you got to be careful. And so having an important understanding of where things are, is it in the stack, in the heap space, whatever, did I know what compile time versus runtime? These are important problems that we need to consider. Now, if this is Java, we don't need to care because the high-level programming language is dealing with that for us, which is a good thing. We like that. So, the stack. Now, you might say, yeah, but Java, there's some overhead associated, like a runtime processing power, energy, literally energy associated with going and deleting or knowing what can and can't be overwritten, right? And that's absolutely true. Where in C++, you save that energy. You save that computing power to know, like if you offload the work where me as the programmer says, go and delete this chunk of RAM, the computer doesn't need to think about it, right? So, there's always a trade-off. Now, often when you're using modern hardware in a world like today with high-level languages, we don't really like to think about that type of stuff. You can make an engineering argument for why this is really important, why you should, but at the end of the day, the issue of allocating and deallocating RAM is not really, and this might sound like I'm grasping here, but this is really true. Allocating and deallocating RAM is a consequence of how our computers work, and not a consequence of computation as defined within the universe, right? As a series of steps to solve a problem. I don't give a shit how it's encoded and what's it stored on, and RAM, zeros of transistors. Has transistors, I can't say it has nothing to do with computing, because obviously it enables computing like we know it today, but they are not the same, like how we compute on our modern computers and computing are very different things. Anyways, back to the topic. So, the stack. This stores information about the current method being run. And really it stores the information of all the methods that are currently being run. Because if I have a method that calls a method that calls a method that calls a method, and this method calls another method, this one can't finish until this one finishes, it returns. So like it actually stores all that information, but the stack. It stores information about the current method and methods being run, like the things like the local variables, formal parameters, that's like your parameter list, your return address, like basically if I'm in a chunk of RAM, remember the instructions are in RAM. If I'm on memory address whatever, I'm on memory address 101, and that says go run this function located in memory address 201. When that function finishes, the computer needs to know where to go back to, 101. So it needs to know where to return to. So there's the stack, which, by the way, the stack is a stack. And sometimes you'll see the word pushdown to mean stack. That's more of like an old school word for a stack, but it's a stack. And then there's the heap. The heap, by the way, can be broken down into two smaller parts. I said RAM can be broken down to broad parts, stack and the heap, but the heap itself is often broken down into two other parts, the static information and instance information. So static information, that's like stuff that's like your program code. And then instance information. This is going to have things like your instances of objects and whatnot, things that are like created dynamically and whatnot, but references to them. And technically we can break this down into even more, but we're not going to go there, okay? Like there's a hierarchy on how long things have existed for the sake of garbage collection. So we have a chunk of memory that has like a stack, which I've represented as this like series of boxes. It's a stack, so it can grow and shrink from one side. And it has references to things, the objects in the heap, right? So let's say in here, my current method creates a variable called I need an array, and it creates a new array. Well, the array lives here, but the reference to the array lives here. Okay? Yeah? Okay? Yeah. And sometimes these objects will have references to other objects, right? So not all reference objects have to exist in the stack. They could exist in here, right? Like if I have a bag that has a reference to an array, yeah, it's going to have this kind of thing. And then down here in the blue part is a chunk of RAM. Well, this is like the static part of the heap. This is like your instructions and objects code and whatnot, okay? Cool. So there we go, great. So, for example, calling bag my bag equals new bag, the information on what an array bag is stored in the static area of the heap. The array sorted bag instance that's created is put in the instance area of the heap, and a reference variable my bag will be stored in the, assuming this was put in like a main method, this would be in some other method. It was created somewhere. The variable my bag would be stored presumably in the stack somewhere. Let's say it's in the main method, okay? So it all kind of goes to its nice, neat, and tidy place. Now, the call stack is a part of memory where the information about the current method being stored. Now, really, it stores all the other methods' information that's running, okay? I've got a little GIF here, right? You laugh at that because I say it annoys everybody. If I have a method that calls another, you know what, give me a moment. You know what, let's call it here because I don't want to start this with less than 2 minutes left. Any last questions before we wrap up today? All right, cool. I'll see you all later.